Welcome to today's lecture. Are you familiar with the old saying, a picture is worth 1,000 words? Well, even though this is how most of us think of this saying, the actual quotation is one picture is worth 10,000 words. Frederick R. Barnard said this in Printer's Ink on December 8, 1921. Since we're going to be spending a large portion of the lesson discussing flowcharting, I believe Barnard's quotation is very relevant. While flowcharts are a fine tool for defining processes, they also help us analyze what's taking place. We'll look at the ins and outs and the subtleties of creating and using flowcharts. After we discuss flowcharting, we'll jump back into the world of statistics. I bet some of you thought we were finished with that stuff. By now, you probably realize that quality has a large statistical component. Without any further delay, let's enter the world of flowcharting. If you want to gain knowledge by analyzing and flowcharting a process, it's essential that you understand the scope. How big is it? Do I need one sheet or paper or 100? The steps, what's happening, and in what sequence, and the relationships. Which steps must happen before others can occur? The purpose of a flowchart is to create a graphical or visual representation of a process. The use of flowcharts provides some significant benefits. For starters, it increases your understanding of a process. Theoretically, you need to understand something before you begin to work on it. But we know that many people, especially the ones that love to tamper with processes, don't believe or follow this. A few years ago, I helped diagram a process that began with internal users' needs and ended with receiving materials or services. I worked with members of the purchasing department. It was difficult to get past the first few boxes because too many people had different levels of understanding or interpretations about what was occurring. Once we completed our flowchart, everyone had a much better understanding. When we created a picture with symbols, lines, and labels, we overcame semantic and interpretive differences. Although helpful, I'm not a stickler for using a certain kind of circle, box, triangle, or diamond when you construct your flowchart. For purposes of process improvement, I think this is secondary. Next, flowcharts clearly define wasteful or duplicate process steps. Referring back to my purchasing flowchart, after we completed page 1, it was clear that 2 buyer's assistants were performing duplicate work, checking signature authority for the person signing a requisition. Also, they were making and filing extra copies of purchase orders that no one ever reviewed. Another outstanding benefit of flowcharts is simplifying written procedures. Many departments no longer use page upon page of documented procedures. Their preference is a single page cover sheet backed with 1 or 2 pages of flowcharts. Let's spend a bit of time and go through a step-by-step overview regarding the construction of a flowchart. If you follow these basic process steps, you'll be in good shape. First, determine the process that you want to work on. Make sure that you don't succumb to scope creep. Scope creep rears its head when you begin to flowchart a certain process and then unintentionally end up flowcharting your entire company. I think that all of us have experienced scope creep at one time or another. Number 2 is decide on the level of detail you need. This is critical. Do you need a 10,000-foot level flowchart, something that can be seen from an airplane? Or do you need one that is from 100-foot level, the view from the top of a building? These 2 views are examples of macro or micro flowcharting. For example, let's consider what takes place in an order entry department. A customer calls, the representative takes the order and forwards it to the warehouse for filing. That's a macro process. If you focus on what a representative does to receive and forward an order, it's a micro process. Number 3, determine the process steps. Brainstorming will help you accomplish this. At this stage, you don't need to sequence process steps. Your objective is to obtain all the steps that you believe are taking place. Number 4, sequence the process steps. Arrange the steps in the order they occur. Use your flow charting symbols here. I think that boxes for basic process steps, diamonds for decisions, yes or no, and lines with arrowheads are sufficient. Number 5, compare the flow chart to the actual process in real time to verify accuracy. A good way to do this is to give your flow chart to a process owner performing a task or activity. Number 6, identify and target steps for improvement or elimination. Make sure to do this with your team. Before we talk about a couple of special types of flowcharts, let's look at some challenges that you may encounter when you want to make a flowchart. Despite the relative ease of making a flowchart, you need to be aware of a few obstacles. First, your process may not be stable. By this, I mean it doesn't happen the same way each time. This is not that unlikely. Should you encounter this, try to define it the way you believe it is occurring or how it works the majority of the time. Of course, you should also do your best to stabilize it so that it becomes predictable. Another challenge is that a process may be so complex it's difficult to gain an understanding. My advice is to start small by just performing flowcharting on a portion of the process. The last issue deals with some participants being dishonest regarding what they know. This could happen if they feel threatened by the outcome of the flowcharting exercise. Okay, let's talk about two special types of flowcharts. To the right, you have a deployment or integrated flowcharts. Integrated flowcharts, also known as deployment flowcharts, are extremely helpful. They're called deployment flowcharts because tasks are deployed, transmitted across department lines. They take a basic flowchart and expand it in a unique way. Not only do these types of flowcharts show the process flow, they also reflect which department or individual has responsibility for a task. This is useful when a process has hundreds of steps and it passes through multiple departments, like many processes do. Integrated flowcharts can identify which department is performing the greatest number of process steps. Integrated flowcharts help plan human resources. Also, they identify convoluted paths, as is the case when part of a process flows back and forth too often and also unnecessarily. I often combine an integrated flowchart with an infinity diagram. After you write your ideas on cards, you not only arrange them in logical categories, but also in the steps they follow through the various departments. Let's move on to a similar type of flowchart to deployment flowcharts. It's the workflow diagram. Workflow diagrams are even more descriptive than integrated flowcharts. Rather than list the names of departments in columnar fashion across the top of a sheet, you use an actual map or floor diagram. You don't need to use special symbols such as boxes and diamonds. You draw lines between the various areas on the map to indicate the movement of activity. The purpose of the workflow diagram is to try to pinpoint inefficiencies because of unnecessary movements. After you complete the process, it's possible to physically reorganize an area or to re-engineer a process so that it is performed more optimally. Workflow diagrams are particularly effective for organizations that are moving to a new facility. As part of the planning process, they construct a workflow diagram to indicate the relationships between each department. This will help determine the location for each department in the new facility. I hope our discussion of flowcharts was helpful. Let's move on to hypothesis testing. A hypothesis is an interpretation of a condition that helps a decision maker take action. As applied to the subject of this course, a statistical hypothesis is a claim or a belief about a value that is not known. For example, a manager may advocate a new work schedule because she believes that 90% of employees favor it. The manager doesn't have hard data. Her beliefs and estimates come from employee conversations and her own opinions of the benefits of the new schedule compared to the existing one. Think of hypotheses as special types of questions about population parameters, such as means, spread, and frequency. Since a hypothesis is an assumption, you need to test it. If you want a certain level of accuracy, estimates are not good enough. Suppose that we toss a coin 20 times and each time it turns up tails. Would you question the authenticity of this coin? I would. From a statistics perspective, the chances of the coin coming up tails each time is extremely low. I hope you recognize this as a binomial distribution because it is an either-or situation, heads or tails. The probability of 20 tails out of 20 tosses is 1 divided by 2 to the 20th power, which is 0.000000095367. This is not too likely. For this type of situation, we have two choices. We can either accept the coin as legitimate and believe that we're facing a very unusual situation, or we could say that the coin is a fake, that it is biased. Since the probability of 20 tails out of 20 tosses is less than 0.001, I think it's safe to believe that we're dealing with a fake coin. When you work with a hypothesis, you begin by evaluating two states, a null hypothesis and an alternative hypothesis. You may remember these terms from a science class. Null and alternative hypotheses are the starting points for most experiments. Another place to observe these hypotheses is in a courtroom. A judge instructs a jury to assume a defendant is not guilty unless there is sufficient evidence that indicates otherwise. The judge's instruction is an example of the null hypothesis. Suppose that I want to develop a new work schedule. I want to involve many employees and do some benchmarking. I believe there are different levels of productivity depending on the day of the week. In fact, this is my alternative hypothesis. But before I invest time on my new schedule, I need to test the null hypothesis, which is the days of the week have no effect on productivity. If I find this to be the case, I accept the null hypothesis and cancel my plans for the new schedule. For the coin toss experiment, we could say that our null hypothesis is that the coin toss is fair because the coin is legitimate, meaning that the probability of getting a head or tail is 50%. However, after we completed the 20th toss, we decide to reject the null hypothesis, and we do it at the 0.001 level of significance, which is a rounding off of the true probability we just identified, 0.00000095367. Levels of significance in statistics are 0.001, 0.01, 0.05, and 0.10. Occasionally, decision makers make the wrong decisions when they use hypotheses. They may accept a hypothesis when they should reject it, or they reject a hypothesis when they should accept it. What we have at the bottom of the slide here is an example. Suppose my business associate, Robin, is developing a new product. He determines that he must have at least 5,000 customers to make an acceptable rate of return. The null hypothesis is that the customers are less than 5,000, and the alternative hypothesis is that customers exceed 5,000. Robin sets up a simple decision table that communicates his choices. If Robin markets the product, has less than 5,000 customers, and rejects the null hypothesis, this is the wrong decision. This is called a type 1 error, also known as an alpha error. On the other hand, if he rejects the alternative hypothesis when he has more than 5,000, this is also a wrong decision. This is called a type 2 error, also known as a beta error. When we test alternative hypotheses, they can be either one-sided or two-sided. Robin's new product is a one-sided problem. If he suffers a type 1 error, he has a one-sided problem because he has less than 5,000 customers. Suppose we're asked to make a special portion of a product for a testing laboratory. The lab needs exactly 7 ounces of this product. We use a 10-ounce bottle because suppliers don't make 7-ounce bottles. We develop a hypothesis that states the process mean is 7 ounces. Our hypothesis is two-sided because we may have a problem if the fill volume is greater than or less than 7 ounces. Let's move on to our final topic for this lecture, analysis of variance, known as ANOVA. Analysis of variance, or ANOVA, originally helped agricultural researchers determine the effects of fertilizers on crop yields. It is used popularly today in many fields. ANOVA is a powerful tool. It separates variation into independent components so you can test hypotheses. When you separate variation, called partitions, in ANOVA terminology, you can estimate the contributions of various factors which may cause variation. Partitioning total variation helps you determine variation due to differences in processes or populations and variation due to random events. To use ANOVA, you need to assume that samples are random and independent, that populations are normal, and populations have the same variance. If you can't realistically make these assumptions, you need to consider another technique. The thrust of ANOVA is to develop a statistic that examines variation among samples and within samples. The ratio of these samples, called a F statistic or F ratio, reflects the location of variation. If the ratio is large, the variation among the samples is much larger in comparison to the variation within the samples. To use ANOVA, you either need a good grasp of intermediate statistics or you need to use a computer program. Computer programs for ANOVA are readily available and quite similar. Once you set up your problem and input basic data, the program produces the results you're looking for. For the remainder of this lesson, I'll only be able to scratch the surface for ANOVA. Hopefully, you'll get a feel for how it works. Let's look at an example. Always Ready, AR, battery company, makes 2 brands of AA batteries, Classic and Zygo. Sales are booming because of demand for these types of batteries. Always Ready wants us to help them understand the differences for the useful life between their AA batteries. We decide to do this by seeing if there is a difference between the mean battery lives, and we go to the facility to collect some data. The first thing we do is to create a null hypothesis. It's the following. There is no difference between the population means for Classic and Zygo batteries. When we arrive at the company, we take 6 randomly drawn samples from each brand and find the following useful lives expressed in hours that you could see at the very top of your screen. First, we need to find the sum of the squares for each process. It's equal to the number of samples for Classic times the number of samples for Zygo divided by the number of samples for Classic plus the number of samples for Zygo multiplied by the mean time for the Classic samples, YA, and the Zygo samples, YB squared. So mathematically, you can see the formula in the middle of your slide here, which we described. Now, if we substitute our values in terms of the means into the formula, we get the following result, which is 1.6875. Next, we need to find the sum of squares of deviations. To do this, we first subtract the mean of YA from each sample of Classic and square the result, which we see in the first 2 columns in the table at the right. Then we add all the results. We also do the same thing for Zygo. Then what we do is we look at the sum of squared errors, which is the formula there at the bottom right, and we find out it's 5.8617, which we get by adding the 2.78633 and the 3.07333, which are the totals in the tables. We then convert these two statistics to our F statistic, which equals the mean square for the processes divided by the mean square for the error, which is MST divided by MSC. Calculating the rest of the problem is beyond the scope of this lesson, but it involves using variance to come up with MSC and also using a value from the F distribution table. Ultimately, our F statistic is 2.88, which is not high enough to allow us to reject the null hypothesis. We'll have to keep working to come up with an answer for the company that we're helping. This concludes our lecture for today. I hope all of you are doing well, and I look forward to talking to you next time.